Hi guys, and welcome to this presentation. I'm Cioppa from the University of Liège, and today we will show you how you can perform at best on changing domains by combining your deep learning models on the fly. This is a joint work of the Trail team with Sébastien, myself, Anaïs, Renaud, Maxime, Benoît, Saïd, and Marc from 3 Belgian universities. Let's go! Alright, so imagine that you just got a brand new fully autonomous car using deep learning to analyze its environment and make the right decisions to keep you safe. This may, for instance, include semantic segmentation of the scene, which consists in assigning a unique label to each pixel. This kind of scene analysis is critical for important downstream tasks such as steering or adjusting the speed of the vehicle in response to external hazards. However, it is extremely complicated to build a single model that fits any possible situation and environment that we call domains. For instance, if it suddenly starts snowing heavily, or if your car drives to another country with different road signs, the model may simply be unable to adapt on the fly, which can have catastrophic consequences. To overcome this issue, we present a novel algorithm that, rather than relying on a single big model containing all the information, combines the posteriors of different source models trained on specific domains. But that's not the best part. We don't just provide any algorithm. We mathematically prove that this is the exact solution to the mixture domain adaptation problem, in which the target domain can be expressed as a convex combination of the source domains. In other words, this means that the target domain is characterized as the mixture of possible situations in the source domains. Now, this requires a lot of math and a probabilistic framework that we will leave out of this presentation, but feel free to check the paper for the details. Let us rather explain our algorithm through a synthetic example. Let us consider a first domain during daytime with a bright sun. We can collect data on this particular domain and train a segmentation model that should produce some good results on new videos taken on the same domain. Now, we can do the same on a second domain during daytime as well, but with falling rain and fog instead of sun. We can train a second model on this new domain, which should also produce some good results on videos taken on this rain domain. Alright, so now let's motivate why we need domain adaptation. What would happen if we test the model trained on the sun domain with videos from the rain domain? Well, as you can see, the model's segmentation masks are clearly suboptimal, and the same phenomenon happens if we test the rain domain model on sun videos. At any moment, your intelligent car is aware of current time and knows that it is driving during the day, and it is also connected to an online weather service and knows the proportion of rain and fog it expects to encounter in the near future. This knowledge implies that the current domain, known as the target domain, is dynamically changing. In this case, the target domain is a mixture of two source domains. For the sake of visualization, we depict such a domain by setting side by side the two source domains, the position of the cut giving the mixture weights that we call lambda, starting from 0 to 100%. When lambda is equal to 0, we are in the sun domain, and when lambda is equal to 100, we are in the rain domain. In practice, this situation would be a bit different. The car would rather pass through different domains over time, for instance when the weather changes. But our example is more visually compelling and still holds the same principle. Now, we can test our first model trained on the sun domain on this new mixture video and see the results. As expected, the model works well on the sun part, but not on the rain part. The inverse is also true. If we use the rain model, it works well on the rain part, but not on the sun part. One simple heuristic that one might think of is to use both models and randomly choose one or the other's output following the probability given by lambda. In practice, this heuristic is always suboptimal. Instead of selecting the decisions of the models, we could also linearly combine the posteriors given by the models, which are sometimes called the confidence scores of each semantic class. For that, we can simply perform a weighted sum of the posteriors with respect to lambda. Now in practice, this works better than using either of the models. However, the output is not optimal and we can do better. In this paper, we mathematically prove that the exact solution exists, and this is how to do it. First, you will need to train or collect one segmentation model per source domain. The output of those models are the posteriors of each semantic class per pixel. Next, you will need to train a domain discriminator model whose role will be for each pixel to predict the probability of belonging to a specific domain. Once you have gathered the posteriors of each source model, you can pass them through a target shift that aims at expressing the posteriors with respect to the right priors, or, if you prefer, with respect to the right distribution of the semantic classes. Afterwards, perform the same operation on the posteriors of the domain discriminator, but using the lambda values instead of the semantic class distribution. Finally, to obtain the final posterior, the probability theory says that you just have to do a weighted sum of the target-shifted posteriors, where the weights are given by the target-shifted domain discriminator posteriors. But I draw your attention on the fact that this has nothing to do with the heuristic in which we weighted them by lambda. That was a lot of math, but don't worry, we provide a GPU implementation on GitHub. One main advantage of our algorithm is that everything is updated on the fly, without having to retrain the models, but simply by changing the lambda values. This gives it a lot of flexibility. A second advantage is that we only need the source and domain discriminator models and their training distribution. This means that our algorithm could be used by several distinct entities sharing models among themselves, where only a few unlabeled data need to be shared to train a discriminator model. Now that you know how our algorithm works, let's see some more practical examples on real data. In the first example, we use videos from the cityscapes and the BDD 100K datasets as the source domains that are taken in different places. We created the target domain as a mixture by weighting the images according to lambda. Our mixture represents a user who would move between different places. As you can see, a model trained on cityscapes is clearly suboptimal on BDD 100K and vice versa. Again, this shows the need for domain adaptation in real-world computer vision applications. Combining the decisions of the models performs poorly, and combining the posteriors a little better. However, combining the posteriors with our algorithm outperforms all heuristics. We also tested the same setup with 4 surveillance datasets and averaged the performance over all possible target domains. We show better performance on average when combining the posteriors with our algorithm. So if you don't know where your next video surveillance camera is going to be installed, our algorithm is the solution you are looking for. As a last result, we tested our algorithm to see its performance when the target domain is not a mixture of the source domains, but a linear combination of the parameters of the source domain. So in the case of the synthetic dataset, this would mean progressively adding more rain instead of having full sun or full rain. This case does not respect our assumptions, but it is indeed interesting to observe to which extent our algorithm also works well. We trained 4 models on 4 source domains: daylight and sunny, daylight, rainy and foggy, night and no rain, night, rainy and foggy. We can see that when the target domain's parameters changes, our algorithm can also adapt on the fly to produce better segmentation masks. Alright, so let's sum up our take-home messages. First, don't combine the decisions of the model, but rather the posteriors for the mixture domain adaptation problem. And 2, our algorithm is interpretable thanks to the probability theory. As you've seen, our pipeline is completely generic and may be used for all kinds of models and all kinds of tasks. I'm sure that you will be able to use it on your own projects. For the mathematical details, feel free to check our paper, and our code is available on GitHub. Well, I hope you enjoyed this video. If you want to know more about the work we do in our lab, make sure to subscribe to this YouTube channel. If you have any question, please contact any of our team members or leave a comment down below. Thank you and see you next time.